I believe this is the 9th lecture in the series, and this morning I'm going to talk to you about how to characterize the materials that you made. And it'll be very basic, but I think that going through the basic elements is important because they're often kind of missed out on, especially when you start to think about, you made your material and then you just, the characterization part is really simple because there's some machine that does it and you push a button or usually click a mouse and say, tell the machine to do it. A lot of times that machine doesn't quite do it the way it needs to be done, and you can easily get results that are not really valid. And I want you to understand what the machine is doing so that you can control it better. I want to also acknowledge the content of this lecture is, largely comes from a group of collaborators that I've had over the years back at Purdue. And in particular, I have to call out Professor Ron Reifenberger. He's a physics professor, but he really thinks like an engineer. And so a lot of the material that I'll present today was originally developed by him when he was teaching himself what a supercapacitor does and what it means. And so that's kind of his way of doing things, is to, when he enters a new field, he will write down what he thinks it is, and then he'll investigate that. That's another way of saying that often the best way to learn about something is to teach it, right? It's best for the teacher learner, maybe not so much for just the learners, but here goes. I wanted to give you a little bit of a sense of time in capacitors. So capacitance in general is, and this is, I'm not sure we've even said this yet, but in general capacitance is proportional to a dielectric constant, we'll call that kappa, and area. So the more area, the more capacitance. And then D is the separation between your electrodes. Okay, so historically, capacitors started out way back in the 1750s with oxide materials, and that was when materials weren't really a field of study at all. It was all just sort of coming together, and we didn't even really understand what fluids were. Even the air that people breathed was not really well understood, but they were able to show that some of these materials had interesting electrical characteristics, and that in essence they could store charge, even though charge itself was not really well understood at the time. Then in the early 1900s, people started to put things together and kind of package materials together, like Professor Gupta just lectured about. Gave a very nice talk about how you actually put these things together. And you could see that the processes that are used today in the laboratory are not too different than those that someone in the 1920s would have access to. Maybe a little bit more fancy cutting tools and things like that, but really putting layered materials together. When that happened, they were controlling the distance between the plates, between the electrodes, and the capacitances then increased significantly. Then moving on to the 1970s, there's a big gap there, right? From the 1920s to the 1970s, I suppose a few things happened, but the big new thing that came in the 70s was that people started to use carbon, and nanostructured carbon in particular, although they didn't call it that then. Excuse me. And they were able to affect the area part of the capacitance equation, right? So very, very high area. And that led to orders of magnitude increases in capacitance, in total capacitance, where you start to get up to things like 10 farads, which today you could go into a laboratory and without too much trouble take some carbon material, take some KOH, some water, maybe a little bit of a separator, some kind of a membrane. Even tissue could be your membrane, and you could make a 10 farad capacitor without too much trouble, right? But they didn't really understand all these things, and most of that ability to go up to very high capacitances comes from the fact that you can have very high surface area. And then in the 90s and to today, we have pseudo capacitance. This is where we add some special chemistry to the surface that allows us to bolster the double layer capacitance, and that puts us into the up to 1,000 farads, into that kind of range. And that's when you're at 1,000 farads, then you're talking about something that could be used at an industrial scale. Okay. So you've seen pictures, versions of this picture, maybe this exact one before. Dr. Gupta gave a summary of it earlier today, but I want to just emphasize it some more in your minds, what the structure of these devices looks like. In general, when you have a double layer capacitor, you really have two capacitors in one, and you end up with a structure, a heterogeneous structure, where you have a charge collector, some kind of layer, an active layer of material on top and bottom, and then you have positive and negative charges that move through the electrolyte. You have a separator in between to make sure that essentially that the two sides don't short with each other. Okay? And what you'd like to do when you look at a device like this is you'd like to be able to test it not only for its basic characteristics, but also for how well it holds up to stress. And stress could come in a number of different forms. We won't talk about that in this lecture, but tomorrow's will, where you talk about cycles. Cycles can stress a material. Voltage can stress a material. Temperature can stress a material. And so the point of this lecture is not to talk about those aging tests or those reliability tests, but it's to get you to recognize that in order to understand the reliability of what you've made, you have to run these characterization tests very routinely. Okay, so you have to know what you're doing and do it the same way every time if you want to develop an idea of the trend. So as we move from double layer capacitors to the supercapacitor, in essence what happens is that you take a micro porous layer. You have typically a huge surface area. So for example, 1,000, order of magnitude, 1,000 meters squared per gram. 1,000 meters squared. Try to imagine what that is in your mind, okay? And how that would look spread out in front of you. And then you say, I'm going to put that much area in 1 gram. It's amazing, really. It's amazing. If we think about graphene, we were talking about, there are people that talk about making graphene at the ton scale, right? Well, if you make a ton of graphene, you should go ahead and calculate how much surface area would that be. And the scale of making a ton of graphene, actually, when the length scale of making a ton of graphene, you have to start thinking about global length scales. You can cover big chunks of the earth with a ton of graphene. It's amazing. You also, in making a high surface area material, you have to recognize that what you're also doing is creating channels for charge transport. That's good in one way because every channel, extra channel that you make is more surface area, but it also introduces some resistance. It introduces some resistance to the flow of charge. And so it's not all good because resistance is something we don't want. As soon as you send current through a resistor, that energy is going to transform itself. Part of that energy is going to transform itself into heat. And then heat is not something that you can use in a useful way, right? In fact, it's just dissipated. I'll give an entire lecture about thermal effects in these devices. But what you can do when you do have nanopores is you could make a transmission line type of model where you have a sequence of resistors and capacitors that represent that process of charge flow into a pore. And in that case, you have not only just these two capacitors inside of an overall capacitor that I talked about before, but you have small effective capacitors along the wall of your porosity. And here's again something on pseudocapacitance. You can make this layer, you can take this high surface area, and if you can find a way to coat that high surface area with a material, and remember yesterday we said that pseudocapacitance effects happen only in the first nanometer or so of the material. So you have to find a way to coat your electrode with something very, very thin and very uniform in order to get high performance. And what happens in here, typically we have oxidation reduction reactions. There are other things that can happen too. You could engineer some sort of electroabsorption. That's when charge actually binds to the surface, or intercalation processes. Intercalation is what happens in a battery. That's where the ion actually penetrates into the lattice of the material. And that's why we use graphite a lot, because it has these loose layers in between the graphene planes, and that allows for intercalation of ions. So the nice thing about supercapacitors is that you can get millions of cycles out of them. And we talked about some of the energy considerations. We do need to bolster supercapacitors. We tend to have to go to multiple stacks of individual capacitors in order to achieve a high voltage. I mentioned that yesterday. You can have very, very high charge and discharge rates. And we'll talk about that some more today. The reason is that, in part, you make these supercapacitors very thin, and therefore they have low series resistance, and that low resistance allows for high for high rates. You can have this high power density, 1,000 watts per kilogram, order of magnitude. Also, you should think about that. How much power is 1,000 watts per kilogram? Right? Your automobile puts out, dozens of kilowatts, right? And so with just a dozen or so kilograms of this material, you could produce enough power to move the car. That's not very much, it seems to me. In general, supercapacitors have an advantage over batteries in that they don't use a lot of toxic materials. Typically, there are some that do. And so when the supercapacitor breaks or undergoes a very high temperature condition, usually it's not leaching out damaging components, environmentally damaging components. And so it's easier to contain. And then it also, supercapacitors tend to be more friendly for temperature extremes, and I'll have an entire lecture about that as well coming up. But you can go to very, very high temperatures. So here in Jodhpur, right, you could be operating in the hottest day of summer, which I'm told is near 50 degrees C, which is, wow, that's really, really hot. I don't know how you can even do anything when it's that hot outside. But more common to me, or familiar to me, is the minus 40 degrees C, right? And neither of those temperatures are suitable for most batteries, but supercapacitors can handle them pretty well. All right, so I'm going to go through a few slides on measurements, and I'm going to focus on supercapacitors. I apologize if you're looking for batteries. Yesterday we talked about voltage curves, voltage discharge curves for batteries, and we'll pick up some other ideas about batteries as we go. But most of what I talk about is going to be on supercapacitors. So what we would do, the first thing that's typically done for supercapacitors, let's say an electrode, is that you take the electrode and you put it into some kind of a cell, usually a 3-electrode cell, and you sweep the voltage over the cell, okay, typically in a linear rate with respect to time. So you have some kind of a voltage increase with time that's constant, and then you sweep back at the same rate, and you're looking for measuring the current as a function of that voltage, okay? And so you do this Again, the fact that you do it at a constant rate, that is the time derivative of voltage. It's in the denominator of the yellow box here. You do that at a constant rate. The capacitance is actually just the current that you measure divided by that sweep rate, that voltage rate. And so if you have a perfect capacitor, a perfect double layer capacitor, what you would find, meaning that you don't have any extra resistances or anything like that, is you would find that you have a perfect rectangle. And all that would happen as you increase the rate, you do one test with a full sweep from high voltage to low voltage, or from positive voltage to negative voltage and back. You do one full cycle of that and you will end up with a rectangle. What would happen if you did the same voltage range at a different rate? The only thing that would happen is the box would get bigger, right? In this chart, because your current would increase at a higher sweep rate because you have a single capacitance here, okay? That's the only thing that would change. Now, in reality, we don't get perfect rectangles, right? Even a ideal double layer capacitor has some internal resistance to it, and once you get the voltage sweep rate high enough, then you'll start to see some smoothing out of the edges of that rectangle, okay? And that's what you see here. This is typical of what you see. This would be a very